Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, today we start our new chapter in operating system, and that is inter-process communication and synchronization. So we have seen that, like we say in the previous lectures, that we have schedulers which actually preempts our processes. What does that mean is we got to have a multi-programming environment, okay, where multiple processes or multiple threads simultaneously concurrently execute. Either they may go a round robin fashion or whatever there is. If there is a multi-processing, we may have the multiple processes going on different computers, different processors simultaneously. Okay, so this is going to be a very important and fundamental feature, okay, where we have concurrent execution of processes or threads. So this will actually we have multi-programming, multi-processing, or distributed systems or client-server models of computation. Now, where multiple processes or threads are concurrently getting executed. Now, with this concurrency, there are many problems. Okay, so we need to have some design issues, like how these processes will communicate with each other and how they will synchronize. Okay, so what does that mean? Because processes may be, which can run independently, which do not need communication with the other process, or they may need the processes are actually interdependent. Now what that means is the process may be independent. That means they don't affect each other execution. So if process 1 or process 2, process 3 comes in and they are working together concurrently, but they are independent processes, then it doesn't matter. So we don't have any issues in executing them together. But if they are cooperating processes, say for example, these three processes are like three people working on a car. Say this P1 is doing some paint, and P2 is doing some tire work, and P3 is doing some mechanical work. Okay, if they are doing on a car, they are working on a car, for example, and they are working on different areas. Say for example, P1 is working on this area, P2 is painting on, say, windows, and P3 is doing on a back something. Okay, now they are working on different areas. They are not interfering with each other, so that they can go concurrently, simultaneously, so there is no issue whatsoever. But consider that in the same car scenario, you are trying, so P1 is trying to paint this area, and where P2 is actually trying to fix it, some mechanical problem or whatever. So now P1 can't, because bonnet will be you have to raise the bonnet in order to get into the car. Now P1 can't paint it because bonnet is open. So that means P1 and P2, they are not independent, they are actually cooperating processes. Okay, so we may have scenarios in our operating system. For example, say P1 and a P2, we and P3, there are many processes going on. We have a single printer, and P1 is trying to print, and P2 is trying to paint, and P3 is trying to print. All the three are trying to print, and when the printer is actually a single printer, so it's non-preemptible resource. Why? Because you can't actually preempt it. When you say, for example, you are doing a round robin scheduling, that means you are giving some time slice to P1, then you preempt it, give it to P2, then give it to P3. Now say in this, when the P1 got the time slice, it tries to print. Now it has printed, say, single line, and it got preempted. Now P2 comes in, it also tries to print. Will this printer now print the line from the P2? And if it's got preempted, then maybe P3 is trying to print. So what will come in a page will be the one line from the P1, second line from P2, third line from P3. So that means this document is destroyed. this is invalid. Okay, so this is a one scenario I'm talking about. So we need the processes to communicate with each other. They need to talk with each other, okay, when they are using some resource, a shareable resource. Okay, so that's why we say the cooperating process can affect or be affected by the execution of another process. So if P1 is executing, now that will affect the P2 as well. So sorry, so we need some kind of communication between them, and also we need, in this case, synchronization, where we have, say, P1 telling P2 that, hey, I got a printer, you can't do it unless I will not finish. Is it or not? It's a clear scenario. Or there may be some kind of a shared variable where P1 is updating that variable. Okay, so there was a shared variable A which is having 10. If P1 is incrementing it to make it 11, and P2 is doing something else to the A, say multiplying it with the 2, and P3 is dividing this A, say for example. Now when P1 comes back after preempting, it will find a total different value. So we need some kind of communication between them so that they will understand what they are doing. So there are clear advantages of process cooperation, that you can share the information among the processes. Okay, you know, you can have a computation speed up. It will really speed up the computation because different processes can work together now, and there's a modularity, there's a convenience. Okay, modularity in the sense that different processes are working together, so you have a modular structure. If P1 has something, some IO to do, you can do another process in the meantime, and so on. So you can have a modular structure in programming and all those things, and there is a convenience as well. But at the same time, it can lead us to some dangers like data corruption, like in this case. There can be deadlocks, which you take up as a chapter later on. Okay, and it will have definitely the increased complexity because our operating system has to tackle all those things. So which is actually the objective of this chapter. So we need processes to synchronize their processing. So we need a synchronization mechanism, which we talk in detail, right? So these all things come into the parlance of OS now. Now OS was telling to schedule processes. Now there is a problem that we need to communicate with each other. The processes or even threads need to communicate with each other, and also need some kind of synchronization. So what this synchronization is all about, we will talk it in much detail. So what is the purpose of IPC? Definitely it's a data transfer, sharing data. Data transfer means that we have process 1 and process 2 want to share data from process 1 to the process 2, or vice versa, and we can share a same data together. Okay, there is some event notifications that we tell that process P2 something which P2 may be waiting for, say printer, and P1 gives notification. Okay, we can have a resource sharing, and we need to synchronize that. We'll talk this in a detail, and there is some kind of process control as well. So this will all be done using the inter-process communication. Now question is how actually we do the process inter-process communication. That is, we need to talk about the IPC mechanism. So broadly speaking, we can have IPC inter-process communication either with a message passing or using the shared memory. Okay, so message passing, we need to have message passing interface. We have mailboxes. So we got a mailbox, and P1 can write to the mailbox, P2 can read from the mailbox, and so on. We communicate like that. We need to have a message queues as well. We could have a sockets, for example, in the networking. We need to have a socket where we share things. Okay, we can have a streams, we can have a pipes. Okay, now in the shared memory, data is in a shared memory. So we have a shared memory, and process 1, process 2, say process 3 are accessing this shared memory. Okay, so whatever it is, either you use a sockets where you go message passing via sockets, or use shared memory, you need some kind of synchronization. Okay, What does synchronization mean is like I said, we have a shared variable, and if P1 updates it and P2 is using again the shared variable, it again updates it, P3 updates it. So it will I will let me give an example. Say for example you have a bank and you go to the ATM and you go to the bank where there is a clerk on a computer, okay, and there is a particular server where the balance is. Say for example you got $10 in the server, okay, as your balance, bank balance. Now you go to the ATM, you withdraw something, say for example $5, and in this case you go to the you go if you go, say for example simultaneously you went, because I'm talking of the processes which are working simultaneously. If the processes are not working simultaneously or concurrently, then there is no problem of synchronization. So P1 can finish, then P2 comes in, it will work on it, it will finish, then P3 comes in, it will work on it, it will finish, no problem whatsoever. But problem comes when processes come concurrently. So that's what I'm saying. Say you got a process 1 on the ADM and process 2, say for example 2 people go to the bank. This is a bank, and oh, what happened? This is a bank, okay. Now what I'm technically saying is, let me get it a little bit here, okay. Now what I'm saying is, you got on a server you got $10, for example, your balance, and 2 people come simultaneously. One go to the ATM, one go to the bank to submit $5, okay, and P1 want to withdraw $5. When P1 and P2 came simultaneously, it goes to the ATM machine asks server what is the balance. It comes in its local RAM in an ATM as $10. Same is with the P2. A clerk at the bank sees on his terminal, it fetches data from the server. So this is a same shared thing, and it also says, hey, I got $10 as a balance. Now what will happen is you are submitting the $5, so total is 15. In a local machine you got a $15, and this guy is withdrawing from the balance, so you got 10 minus 5, that is $5 as a total. Now say for example this ADM guy update this server, because it thinks it's the only guy who is accessing it, so it says, hey, it's not now $10, it is $5. Now after this one updates, and it says now, hey, it was not whatever it is $15, so it updates as a $15. So because it thinks that $10 I had in the bank, now I submitted 5, so I got a 15. What about the ATM guy? So that's lost, that information is lost. Or in other words, if this guy first updates as a $15 in a server, okay, later on this updates, it cuts it to $5. So that means what you are submitting $5, that is gone. So this can't be done like this. So otherwise it will be like, mess in your banks. So banking is not going to work. So what we do is we need some kind of locking, a synchronization between these two processes, process 1 and process 2. We got to tell them, hey, I'm using this server, I have done it, I'm using this balance, I'm doing it, okay. You can't access it right now because I am updating, I'm in a process to update this. When I'm done, when ATM process is done, now you can do it, now it's your turn. It can be like that, okay. So that's what's called as a mutex. So we have to use some kind of synchronization mechanism, or mutex, or in shorts mutex, mutual exclusion. That means this have to be done by the ATM machine first, then this bank guy can do it, or vice versa, or some kind of waiting you can do, okay. So for example, I gave the example of a printer. So we have a single printer, P1 is trying to print, and then P2 and P3, they're all trying to print. When P1 is printing, and you are actually in a multiprocessor system or multi-programming environment where you can preempt P1 and load P2, and P2 is trying to print, but in the printer there is a page of process P1. This printer is a non-preemptible resource. It's a non-preemptible resource, so you can't preempt it. Again, We need some kind of synchronization that P1 may lock the printer and do it in its entirety. You have to print the whole page of P1, and then and only then you can go to the P2. Otherwise the page will be messed up, isn't it? So you need some, that's what's called a synchronization, that you are not only communicating with each other, but you are using the mudexes or some kind of varying mechanisms, which we talk in detail later on. We have a lot of algorithms for that. We can do that in a software, in a hardware, and in programming languages. Okay, these synchronization can be done in a software, we can do it in a hardware, we can do it in a programming languages, in OS, and there are a lot of things. We'll talk about all of those things later on. Now let's talk about this message passing and the shared memory stuff. So we're saying message passing, we need a message passing interface, okay, and then we see that we can do it a lot of things like mailboxing or message queues or sockets or streams. So what is actually we are actually trying to say is that we got two processes. Say for example we got a process 1 and we got process 2. They are trying to communicate with each other, okay, and this message passing is all done by the OS. So we have a kernel which is actually doing the stuff, so it is maintained by the OS, okay. So that's a plus of it, okay, because operating system can do its synchronizations and all of its own. So what process 1, when the process 2 need to communicate, basically the kernel will create some kind of a channel, okay, where from you can communicate, where you can pass whatever you want to pass to the P2. And there also need some kind of ports, okay, where from you can this is again a port where from P1 passes something to this channel via the kernel, and then from channel from via this port into the P2, okay. So these ports are actually the interfaces, and these are actually created by the OS itself, okay. And like we have sockets, we know all sockets from networking side, we have done that a lot of times, and like that. So this channel can be some kind of a queue, first in first out queue, or we can simply call it a buffer. These are some buffers where you can put something. So this link will be created by the kernel, the operating system, okay. Then a P1, say for example want to send something to this, so you can have an operation like send operation, or you can say or write operation, okay, where you write something to the port, and where it's not the job of the kernel to apply the synchronization mechanisms and everything, and then it will also have a link, it will also create the link, okay. So you need some system call when you say send or write, because you are talking to the kernel that hey, I want to write something to the port, and from the port it can be taken by the kernel to the port of the P2, okay. So you can typically do two jobs, either you can send or you can receive, okay. So when you are sending, what you are doing is actually you are using a system call to the kernel, okay. Then you actually do what? You copy your data. So I say copy your data into the channel via the port. And in receive also you got a system call firstly, because you got to talk with the kernel, because kernel is the boss, and then you again copy data from the channel into you, right? Now this is little overhead. You have to call the system before you can send, but the thing is that it is very simple, and channel maintenance and channel synchronization is done by the OS itself, so that makes it very simple. Now depending upon how you actually implement this channel, we have what we have we told here that we can do it using the message passing interfaces, mailboxes, message queues, or sockets, or streams, or pipes. So what does that mean is, for example here what I'm talking about, this, say for example the simplest version, this is the process P1 and process P2. Now you're going to want to send something to it, and you are saying that that you create a channel, a dedicated channel from between two processes only. Its input goes into it, okay. So you can then send in a stream of data to the P2. This is what is it called as a pipe. Okay, but this can be done between two processes only. Now if you are doing like this, now this is the pipe. You are using the type pipe in a POSIX like we have. Uh, but you can do it in other way also. Say we have got a P1 and I got a P2. Now you don't have a dedicated pipe, but rather this channel is a kind of a buffer where you can push these and I'm saying this is under the kernel, this is the operating system maintained. So OS may maintain this as, say for example, you put up the message, this is a message, say for example you got another message, you dump it into it and so on, and now this message has to go into it needs to have a perfect format. Okay, so it need to be packaged kind of thing. But here you don't need to package it, you don't need an overhead, you can just go on and send on and send on and send on a pipe. So this is like a message queue, what we talk about, message queue. And the well-known one which we know all is a socket. Now this can be done using a socket API. Okay, you have sockets, and this channel is using the full, in the kernel you can use the TCP IP protocol suites. So all those protocol suites, this is a socket API we'll use here to create a connection with the link, and then use a TCP IP to send from P1 to P2 or vice versa. Right, now you can do that that way also. Now this process P1 and P2 are on the same system, or it may be on a network. So then you are using the full network protocol suite, and that will be done by the kernel again. Okay, this can be done that way also. Now if it is a pipe, then we don't need some proper kind of a message format, but because you need to just a stream of data pass on. But when it is a message passing queue, or it is even a TCP IP socket driven mechanism, we need some kind of message format, right? So now message format will be very important, because if we have P1 and P2 only, then pipe was enough. But maybe there is P2, P3, P4, and you have a communication channel set up by the kernel, right? And you want to send. So now if you're sending message, you may sending it to the, say this message want to go to the P2, another message want to go to the P1, P3, and so on. So how to know which message and this message belongs to whom? Maybe P2 is also want to send. So in the message queue there will be messages of P2, P3, and so on. So how to tell this message belongs to P2 and its destination is P3, say for example, right? So all kind of information is in a message format. Okay, we've got a message type which will tell us actually whose message it is and what kind of message it is. And in Unix we have actually the ID, message ID, which exactly tell us which message it is. Now destination, source, how big is this, because we want to see how big is this so that the next message we can read it without problems. So there's some kind of control information as well. Okay, like the priority, if some messages may have more priority than the other. Okay, it's a control information will be sequence number. Maybe you want to send a message and you are breaking it into the 3 messages. Okay, so you need to have a sequence number. So and you are putting it on the channel. Now they may reach out of order or something like that, so you wanna reassemble it at the destination. So you need to have a control information like sequence number. Okay, or something like if you run out of the buffer space, then what you gotta do? Would you resend all or resend one, or what will do? That all thing comes in a header of the message, and the body will have what actual message. This will be the actual message you want to send, right? So this header is actually the control information which will never make it lost in the channel, right? Now this is the difference between the message queue and a pipe buffer. You can read and write in any size. It's just a stream of data going from one process to another, but limitation is it can be only between two processes. Here we can have multiple processes, and there can be fixed sizes messages, right? And who is gonna sending and who's gonna receiving is in a format of a message itself. Now it's a very complicated thing, the message passing. We can have an RPCs, remote procedure calls as well, and a lot of things, a lot of issues that like how big the channel can be. Is it Like in a pipe, for example, is it a duplex or half duplex, or it can be done, can it be done on network? And there are a lot of issues. I want to cut it short. So we want to talk about now the shared memory IPC. Okay, inter-process connection using shared memory. What in shared memory we do is we got a P1 and we got a P2, for example, the processes. Now they want to send something. What we do is we have the memory, for example, uh, this is my OS kernel, and we have a memory which is managed always by the kernel, right? And we create some space. It need not to be a contiguous. Okay, we can create it anywhere. If this is fill, we can do it on other way, in anywhere we can do it. Now what we do is we have a virtual memory space on the processor side. So we are this is the job of operating system, to create a memory, a virtual memory space. And in fact, it's not here. We are deeming that we have got some kind of memory here, which is not there, which is actually here, right? Say for example, OS calls, say we are trying to access, we want to pass something from P1 to P2. What P want to do is, say it's already in a memory which it want to share. Say it want to share, say here it is written something like hello. So it want to send this hello to the P2. Now what OS does is it creates a virtual address space. Say it says it is at address 123, and it's somewhere else. It's say address at 0x422, for example. Now P1 thinks it's at 123, but it is the OS which keeps it as a virtual address space, and it links that to the actual address, that is 422. So, same with the P2. P2 want to read that hello. Now that was the message which P1 want to send to the P2. Now P2 want to read that hello, and it is not necessary that it will be given the same virtual address 123. It may be given 234, for example, but it is again linked by the OS to the same this memory location, the actual memory location. Now P2 thinks it's its own memory. P1 thinks it's its own memory, but it's not. It's actually virtual memory space here, and it both links to the same memory location in actual physical memory. Now operating system will do what? It will P1 you have to, when you are writing something and you want to send it to P2, the OS actually is doing that, but the copying mechanism is reduced, because if you see the message passing, you have to actually copy whatever you want to send to the channel, then it will go and then copy back to the P2. Now here the copy mechanism is reduced. System calls are there, but the that copy mechanism is reduced, right? So now in a message passing, we had an OS which actually does the synchronization, because the whole thing is maintained by the OS, right? Like I said here, this channel is maintained by the OS, so synchronization is done by the OS. But here both P1 and P2 can access that memory location, right? So the synchronization problem will be there, and this synchronization is not solved by the OS, but it's the job of the programmer now. He has to write program in such a manner that synchronization is met, right? Okay, so it's the responsibility of a programmer now. Now we have both kind of message passing as well as the shared memory. You have a message passing as well as shared memory done by some kind of APIs. Okay, for example, in a POSIX API we can use, or we got a system we got where we can use the message passing, and in shared memory we can also be done by some APIs, like we got a system we got a POSIX API. There is some file based also. So we have a file based APIs also, which can implement these things. Okay, we got what I was talking about, RPCs, remote procedure calls. We can use that later on as well, which we talk about later on in detail. Now in Android also, we have an Android these days. Okay, they have their version of the API called Ashman. They apply this shared memory kind of IPC, inter-process communication. Now, one important point to make between the shared memory and this message passing is that in a message passing we have to use a CPU, CPU cycles to copy. Firstly because there will be system calls, the CPU will be involved, and copying and writing and reading, all done by the CPU, right? In message passing instead, you are mapping this address space here, right? But maybe once you are done with that, now CPU is free. Maybe you are reading it, say 100 times or 200 times, 300 times, whatever times you want to read it. So you can read it without the intervention of CPU cycles. CPU can do other jobs in that way. So that is a very great advantage of the shared memory kind of thing, because here once the addressing is mapped, because that is now very costly, because memory accesses are costlier. But when it is done once, and if it is used for many times, then it will really pay off, right? Because then you don't have to actually use CPU at all, because your addressing is done. You can read it many times you like, right? Now, as an assignment, you got to do one thing. You got to see how the POSIX API or System V API, or we got the Android Ashman and RPCs, and file these APIs, how exactly they apply the message passing, right? This is your assignment, okay? And when you're done, we'll come back to the next video where we talk more about the mutual exclusion. That's actually the synchronization. Now we talk about more on synchronization and its algorithms and everything about it, right? That will be in the next video. And this with that it is now the end of this segment, right? So until next time, ma salama.